Okay, so we're starting with number 7 here with our strong but inept shot putter who puts it straight up. And how long does he have to get out of the way before it hits his head? Right away, something I know about the shot put is that it's in free fall. All right, that's a good place to start. So this is number 7, and the shot put is in. Actually, it's actually not a shot put. Sorry. Ashamed of myself. Call myself a corrector. The shot is in free fall. What does that mean that it's in free fall? Cell equals 9.80 meters per second squared. Which direction? Down. Down. Negative if we say up is positive. Right? So, as the shot goes up, what is it doing? Speeding up, slowing down, or staying at a constant speed? Slowing down on the way up. What does it have to do at the top? Stop. Because it has to turn around. You have to stop to turn around. And then what does it do on the way down? It's accelerating, but I think I heard it. I think I talked over. Speeds up. It speeds up. So remember, slowing down is when your acceleration and your velocity are in opposite directions. Like on the way up, it's moving up, but it's accelerating. It's changing that speed downwards, so it slows down. Stops, and then on the way down, it's moving downwards and accelerating down, so it speeds up. So I would, part of your Y can be a picture. So I'm going to draw it like this and say from here to here, that's slowing. From here to here, it's speeding up. And right here, it is stopped. So velocity equals 0 meters per second. That way it's moving upwards, this way it's moving down. So it's speeding up as it goes down. Did I get my proportions right? Is it going to land at a lower height than what it started at? Yeah. So just looking at that, look at the amount of distance it has to slow down and the amount of distance it has to speed up. Is it going to land on his head moving faster, slower, or the same speed as he released it? Talk to your table for a second. I'm going to pause. Talk to your table. All right, good. Let's look at our problem again, just make sure. Okay. So I know you guys want to do an inventory of the data we know? Yeah? Yep. Yep. Nope. Because if it landed at the same height, like let's look at the situation where it lands and it takes off right at that same height, then it has just as much time to slow down as it has to speed up. So it's going to get to the same speed, and just as much distance to slow down as it has to speed up, so it's going to hit at the exact same speed. It's that extra bit that it gets by going below that causes it to be going faster when it hits him in the head. All right? In fact, at this point, its velocity is positive 12 meters a second. What would it be right at this point, the velocity? Negative 12 meters a second. So all it's done is it's just reversed direction completely. Yep. Exactly. Do you guys want to do an inventory of what we know? Or just go right into the problem? Okay, we'll go right into the problem. So I want to know how long it's going to take to go from the beginning to the end. And I know its initial velocity. I know where it starts. I know where it ends up. I know how it's accelerating. And I want to know how long it takes to go from one place to the other. So I look at my equation sheet, and I just want to zoom in a little bit here. And I look for my equation that tells me about, hey, this is where I started, this is where I end up, and I did some things on the way there, and that's my first equation here, the big, long, pretty one. So I grab that. And now, let me fill in values that I think I know. I end up at 1.70 meters. I started at 2.20 meters. I better move all this over. I know already I'm going to run out of space. There we go. Plus my initial velocity. Which way do you guys want to call? We didn't decide that. Which way do you guys want to call positive? Up? Okay. We're going to call up positive. That means anything that's down, like my acceleration here being down, is going to be negative, right? Right? Okay. So, plus my V initial was upwards, so that's positive 12 meters per second. Delta T plus 1/2 times negative 9.80 meters per second squared. Why is that negative? Because it's down, because the direction is down. Good, excellent. And then delta T squared. Remember, if the deltas really bother you on the T's, you can just drop them and just picture it as T. Cool, I only have one variable left. So now mathematically I can solve it, right? How would you guys approach solving a quadratic like that? How have you been taught to solve that in math class? Huh? PEMDAS? Order of operations? You know how I solve it? I put it into my handy-dandy equation solver down here on the website. And yes, if you get on a test and you're in here, you can go to this to solve this type problem. So let's see, I need to enter that. 1.7 equals 2.2 plus 12 times T. Oh, sorry. 12 times T plus 25 times negative 9.80 parentheses. Yes, I'm listening. Caret 2. So all I've done is typed in that equation that I already had here. 1.7, let's make sure I did it right. 1.7 equals 2.2. 1.7 equals 2.2. 12 times T. 12 meters per second times T. Plus 0.5, which I wrote as 0.5 times negative 9.8 T squared. So I put everything in correctly. I hit my equal sign. Now, it would also work by doing, the exact longhand that you've learned in math. And it tells me that this equation is true for either negative time or positive time. Which one do you think I should take? Positive time. Negative time is just mathematical construct. Not real. So I solve for it, and I get 2.48. And then I would, of course, report that answer to 3 sig figs. So I'd report it as T equals 2.49 seconds. Our shot putter has 2.49 seconds to get out of the way of that shot coming back down. All right, so we're going to talk about number 2 here. That was chosen by 2 of the 5 groups. After that, we just have singletons. So baseball's hit nearly straight up in the air at the speed of this, 22 meters a second. How high does it go? How long is it in the air? Right away, we know because the baseball is just free to move and it's moving. What is it in? Free fall. Yes. So this is number 2. Baseball is in free fall. Therefore, acceleration is little g, and which direction? Which direction is the acceleration in? No, down. Folks, this, I feel it. I know we've gone over this a lot, so it should be like second nature to you. If something's in free fall, it's accelerating at little g, and what do I mean by little g? 9.80 meters per second squared. In which direction? Downwards, always downwards, right? Yes? All right. What else do I know about this ball? What is it? What does it gotta do at the top? Gotta stop at the top. Ooh, that almost like rhymes. Must stop at top. Why is that true? What's it doing at the top? Why is it stopping? Because it has to change directions. Exactly. It must stop at the top since change direction. And there's one assumption we have to make here. And they didn't state it well in the problem. If I wrote the problem for like on your test, I would state it better. Is the baseball needs to land at the same height that it was hit. If it doesn't land at the same height that it was hit, we can't tell how long it was in the air. Unless they tell us something about, if you look at the problem, all they told us is that it went up in the air. With this, we know that it stops at the top, but we don't know, since how long is it in the air, we don't know, does it land, was it hit from the ground and therefore it lands on the ground? Does it fall beyond the ground or what? So we have to assume that it lands at the same, basically the same height it was hit. All right, like you guys did yesterday in lab, right? That's why you were catching it at about the same height that you released it. So I'm going to assume lands where hit. So that's my assumption, that it lands where it was hit, same height it was hit. So, let's see, goes up, comes down, and hits right here. Let's see, you guys told me, or the problem told me it was hit up at 22 meters per second. And you guys told me how fast it's going at the very top. It's not, so that'd be 0 meters per second, right? So which direction is it going to be moving when it hits the ground? Down. How fast is it going to be moving when it hits the ground? 22 meters per second. And we know that, think back to our discussion a few minutes ago, if it goes up this amount and it comes down the same amount, then it's got to change the same. All right? Here it goes from 22, slows down on the way up, gets to 0. On the way down, same acceleration, so it starts at 0 and it speeds up to all the way up to 22. And that's because of my acceleration being downwards and being the same on both sides. All right? So whatever speed, in this case, whatever speed it started at, it went to 0, and then it came back down to that same speed. So I can use all this information I have to now put some numbers with it. Let's see. What do you want to call the position it started at? The position. What number do you want to label the position it started at with? Huh? 0, okay. So we're going to call right here at this level 0 meters. What do you want to call this? What variable? Because we don't know what it is. X. Well, X, a lot of people would read X and think you meant a horizontal. So let's pick something different than X. Why? Because a lot of people... Oh, you meant Y.
Yeah.
Oh. Okay, we'll call it Y. Which way do you guys want to call positive? Up? Call up positive. All right, so we've gotten all our conventions together. Now, I know that it starts at this velocity. I know it ends up at this velocity. I'm wondering how far it had to travel to change from that one velocity to the other velocity. And which equation talks about my velocity changing because I accelerated and traveled? This one here, right? Yep. So that's the one I'm going to pick because that's the one that talks about how those things are related. And this is, so we're only looking at, we're doing part A right now. Let's see, I'll pick a good color. So this is part A. And my V final is 0 meters per second. Math tells me I have to square that. My V initial is 22, positive 22 meters per second. Math tells me I need to square that. Plus 2, negative 9.80 meters per second squared. And then my displacement, my delta D, is how far I go. It's from 0 to Y, which would just be Y. Yes? Everyone see where I got all the things I threw in there? Yes. And as long as I start at 0. Remember, the delta means the change. If I don't start at 0, if I start at like 10, and it's from 10 to whenever, and from whenever. So I'll just have to rely on doing math. So I get 24.7 meters. I get Y equals 24.7 meters. Because I would take that 22 and square it and bring the other stuff on the other side. You guys need me to do the algebra there, or you got the algebra there? So now we have part B, and in part B, it says how long is it in the air? So how long does it take to go from the beginning to the end? And so I know, let's see, there's a couple things you guys told me. It takes the same amount of time to go up as it does to come down. So I could say, hey, let me figure out how long it took to go up and then just double it, right? But I also know it started up, so at positive 22 meters a second, and it ends up coming down at 22 meters a second, so that's negative 22. So I can figure out how much time it took to go from one speed to one velocity to the other, right? And that would be the total time it was in the air. Which way makes more sense? To look at half of the time and double it, or to look at the whole time? Look at half and double it? Okay. Let's look at half and double it. So we're on part B here, blue for B. And I'm saying, okay, it takes a certain amount of time to start at the bottom, go up until its velocity is 0 at the top, and so this relationship tells me about how much time it takes to change my velocity, and this will be half the time, because this would just be the time to go up or just the time to come down, right? So at the top, I'm not moving, so that's 0 meters per second. At the bottom, I was going up, so positive 22 meters per second, plus negative 9.80 meters per second squared times t. See, 9.80 means I'm losing about 10 every second. So about what neighborhood should I get for a value? About what? If I have 22 to get rid of, and every second I get rid of 10, about how long is that going to take me? About 2 seconds. About 2 seconds, because after 1 second I'm going to be going about 10. After 2 seconds I'm going to be going about 0. Right? Huh? You misunderstood. Yeah. You thought it was harder than it was, right? So, the time here, the time to go from the bottom to the top is going to be 2.245 seconds. And that means the total time is twice that, because I've got to not only go from the bottom to the top, but I got to go from the top back down to the bottom. Please stop wasting my tape. In fact, you can put the tape and the scissors back right over there so someone else can find them afterwards. Thank you. It's 4.49 seconds.